Why hello, lovely humans! Jen Foxbot here for part 3 of probability. Jazz hands! Woo! Alright, so in parts 1 and 2 we dealt with discrete situations where you can count the things, but now we are talking about continuous distributions. So that would be something like a probability wave, or something a little bit more tangible. Let's say that instead of wanting to find like the bin numbers of rain, you wanted to find something that was a little bit more continuous like that, where you have a curve instead of hard boundaries. So that's kind of why I wanted to use the rainfall example, is to show you at what point is it useful to use discrete bins and variables, and at what point it might break down. So in this case, when we are dealing with continuous variables, I'm confusing myself now. So the probability of getting a random result between a value of x and a value of x plus a tiny little bit. So remember, dx is called an infinitesimal number, aka it's trying to break things into as small as pieces of, as possible. So instead of a discrete probability, we have a probability density, which is represented by the Greek letter rho, which kind of looks like a lazy P. Letter P. Okay, and so now we can say that the probability of getting a result between A and B, so instead of doing the summation, which deals with discrete quantities, we translate that to the integral, which is summing over all of the things between two given endpoints, in this case A and B. So we sum over the probability density with respect to dx, where maybe x is a distance, but it could really be any amount. It's just a variable, aka a stand-in. And so our probability density must adhere to the fact that if we were to sum over all of space and time or all of the quantities that we are dealing with, for our probability, it would need to equal 1, aka if we, for example, if we expect to find the particle somewhere, it means that we have to find it somewhere. Might not be where we expect, but we have to find it at a certain point. It is going to be somewhere. A couple of other things that we need to define are the average value of our quantity, or the expectation value, aka our quantity with little wings, equals the integral from negative infinity to infinity, and this may change depending on the situation. We will do an example in a second. So you multiply the quantity of interest times the probability density times dx. And again, remember that the expectation value for discrete things is defined to be the summation of that thing times the probability of it. So that's exactly what we have here. We've just kind of translated it for continuous variables. And just a quick aside, if you have a function and you want to find the expectation value, you just kind of plug it on in. So you would really have the same equation, but instead of x, you have some sort of function of x. This works the same way. And then last but definitely not least, we have the variance, which is sigma squared. Standard deviation is sigma, and that equals the square of the averages. Sorry, hold on. The average of the squares. There we go. The average is represented by these wings or these brackets minus the square of the averages. Okay. The average of the squares minus the square of the averages. Okay, so I'm going to erase this so we can do an example. So if you want to save these, you can check out the quantum mechanics book that I am using. This one. Yay, Griffiths. But, or you can take a screenshot. Easy peasy. But do it now, quick. Okay. So now we are going to look at a specific example, because you're like, okay, that's great and fine. That's a lot of equations, but what the heck do they mean? Okay. I am going to take the example straight out of the book. So if you want to follow along, this example is on page 10. We are still just diving into quantum. How cute. Okay, so let's say that I am on top of a building. Woo! Hello! That's me, and I'm gonna get myself some red hair as curly. Okay, and I have a penny. It's a very important object. And let's say I drop it. The building plus my arm is a height h. And I want to figure out what is the average distance of this penny. It's an actually more interesting question because right off the bat we might say, well, h/2, that's the average distance. No, because before I drop the penny, it's not moving. And so right after I drop the penny, it starts out and then it starts speeding up. So in other words, it starts out at rest and it speeds up as it moves downward, aka as it falls, as it moves downwards, also known as falling. So in that case, it's moving slower near the top. It's not covering as much distance as it does near the bottom. So that means that the average height is going to be closer to the top than it is at the bottom, aka it's going to be larger than h/2. Interesting, right? So let's say I get one of my friends to help me, or maybe I rig up a camera so my dog can trigger it, to take pictures at random intervals to help me figure out what the average distance is. So the first thing that we need to do is figure out an equation for the distance of the object, the penny. So that can be represented by the position of the object x is dependent on the time that it travels. So at this point we have t equals 0, x equals h. Sorry, actually we're going to say x equals 0 at the top. And here we have x equals h. And we'll just set t equal to capital T to indicate the final time. So this equation is going to be 1/2 gt squared, where g is the acceleration due to gravity. Okay, so now the second thing that we have to do is we have to figure out, okay, well, the velocity v of x equals dx dt. We just take the derivative with respect to t and we get gt. Okay, and now we're like, wait a second, what is the total time? I want something, using the variables that we are given in this equation, which is not much, but that's okay, we don't need a lot. So, in other words, what is the total fall time, t? So, it turns out that equals square root of 2h/g, and you can figure that out as a quick aside by setting x equal to h, because that's the total distance that our penny is going to travel. So when the penny has hit the ground at a distance of h, our time will be represented by this capital T, and then we can solve for t by multiplying this side by 2, so we have 2h, dividing by g, and then taking the square root to get rid of this pesky square. Boom. Done. Not too bad. Okay, and so now I want to figure out what is the probability that the camera flashes in an interval dt. So don't be too concerned, because really all that is just we're saying, okay, this is the probability of some event happening, right? So in this case, we are asking what is the probability that we have a camera that shows a duration of time represented by this quantity. AKA, we're just looking for a specific probability for each of those camera flashes. So it turns out that that is just divided by the total time, because in this case, n of j is just this, and the total number of things is the total amount of time that we are dealing with. Okay, so then what we can do, we need to find an equation for dt and t in terms of x, because that's our probability density, and that's what we are interested in, is this average height, which is a function of x. And so we just substitute in the values that we have for dt. So we can solve for dt this way by dividing dx by gt. Cool, okay, so we're gonna do that. We're gonna replace dt with dx over gt times 1 over t. So I can do that if I just flip this. That's going to give me a square root of g over 2h. And I can simplify to get 1 over 2 root hx times dx. Okay, so this should be my probability density. I was going to say probability, but since we're dealing with continuous variables, it is a probability density of a particular interval. So this is the probability density in general. We want to make sure that we did this right and that we didn't mix up anything or make any erroneous assumptions. So what we're going to do is we're going to plug this in to the whole situation and make sure that we get a probability of 1. In other words, if we sum this up from 0 to h, we should get 1 because we should find the penny somewhere. So our probability density, we're going to plug in. We get 1 over 2 root hx dx, and then we can solve this to get 1 over 2 root h, 2x to the 1/2 from 0 to h. And I will let you solve this on your own. That is your challenge. That equals 1. So that's good. Whenever you are doing this on your own for a problem that's not in the book, actually, even if it is in the book, you should definitely run through this to make sure that the equation you get for your probability density is correct, because it would not be fun to do all this work and then later find out that it's not the right probability density. Okay, so lastly, now we need to find the average value of the height. So that is represented by bracket x, or x with little wings, and that equals the probability from 0 to h, because we want to find the average over the total distance that our penny traveled, of x times 1 over 2 root h, oh my goodness, hx dx. And in other words, this is going to give us, so x to the 1 plus x to the negative 1/2. Oh, this is confusing. Oh, that's like that. And then multiplied by that fraction. So I'm not going to run through the integral stuff, but I'm happy to give more information if you would like me to. So this ends up as 2 root h times 3/2, sorry, my bad, 2/3 times x to the 3/2, there we go, from 0 to h. And then we can plug in 0 and h to get h over 3. Boom! Look at that. So that's actually pretty interesting, because what that means is that the average height of our penny as it travels from a distance at the top of the building to the bottom of the building is at h over 3. In other words, once it's traveled 1/3 of the distance, that is its average height. It spends more time at the top than it does at the bottom. Pretty cool, right? And all we needed to do all of this math was the height of our the height of our penny, which is just represented by an h, and you can plug in actual numbers here if you are curious about that. So like going to that kind of infamous example, if you were to drop a penny off the Empire State Building, you could say, what is the average height of that object as it fell? Okay, so I hope that this helps understand how to apply the continuous probability density, how to find it, and also how to apply it. So the tricky part is that the probability density is really going to depend on the situation that you're dealing with. And so it's really, really important to understand how to set that up and also to double check that you did it correctly. So when you plug this in over the whole, over all of the possibilities, the probability density over all of the possibilities should be 1. Cool. Okay, so let me know if you have any questions about that. I know that I covered it really quick, but it's super important in quantum mechanics, and hopefully we will be doing a lot of this expectation value type stuff. So just recognize that this is the average expectation value of x. In this case, it means the distance traveled, but it can be really any quantity of interest. Okay, thank you very much for watching. If you like these videos, please support me on Patreon. And thank you so much to our monthly contributors, Christopher M. and Lamore F. Yay! All right, I will see you next time for more Schrodinger's equation. Woo! Bye!